Hello, my name is Rahul Ramachandran. This video is part of the project component for the System Optimization Methods course. I have selected the research option for this project. The domain of interest here is optimization in finance and economics. Optimization in finance can include profit and revenue maximization, portfolio selection, and other such applications. Traditionally, mathematical models are deterministic. Solving optimization problems in this case often overlooks the presence of noise and uncertainties. Operations research applications are a lot more representative of real world situations. They have noise and incomplete data. This is typically solved using some amount of guesswork. The guesswork pertains to guessing the missing values. Another option is to solve for the worst case scenario, which may include contingencies to handle the noise and missing data. Sensitivity analysis is used for solving such operation research problems. In the first paper, titled Robust Optimization for Large Scale Systems, the authors define reactive and proactive approaches to optimization. In the reactive approach, the model is first developed and deployed assuming absence of errors in data. And when the errors are actually introduced, this is when their effect is seen on model output. Instead, the authors suggest a method called proactive or robust optimization. We deal with models with two distinct components. The noise-free input data are called structural components, while for noisy input data, they're called control components. The design variables or structural components are unconditional. Even when certain parameters are realized, they're fixed and hence can be said that they're used to design the model. On the other hand, control components are subject to adjustment once certain parameters are observed. The optimal value as well as realization of uncertain parameters is what defines their values. The optimization problem, thus framed, involves minimizing a C transpose times structural component and D transpose times control component. It also has two equality constraints as shown here. We define a set omega of S scenarios. For each scenario, we associate the set of D, B, C, and E of realizations as coefficients of the control constraints. Each scenario has a probability of P of occurring, and needless to say, the combined probability of the scenarios is 1. The two types of robustness are solution robustness and model robustness. Solution robustness is seen when the optimal solution of the problem is actually close to the optimal solution regardless of the scenario. On the other hand, model robustness is seen if the optimal solution remains feasible for any scenario. The minimization problem we saw in the previous slide is not likely to remain feasible and optimal for all possible scenarios. Hence, a set of control variables is introduced for each scenario. They measure the infeasibility allowed in the control constraints for a specific scenario. The problem discussed so far is now reformulated in this slide. There are multiple functions that can be used as sigma. Here, that is the mean value function. The reformulated model now minimized the maximum value and objective function z. The reformulated problem has two terms. The right term rho is called feasibility penalty function. As its name states, it imposes a penalty when a scenario violates the control constraints. Thus, the entire objective function is of two parts. The first term to measure the robustness of optimality, and the second term to measure model robustness. The term omega in the first term is called goal programming weight. It is used to obtain a range of functions that prefer model robustness to exact solution. The penalty function selection is more often than not problem dependent. Two of these functions are shown in the slide. Mean variance models and expected utility models are the common risk handling models. In a mean variance model, a higher variance indicates large doubt in the outcome. For expected utility models, the result is a concave utility function, more suitable for risk-averse decision making. By maximizing expected utility, a decision maker is essentially displaying consistent behavior. So that was an overview of the first paper. Now we move on to the second one. The paper that we will discuss today is called Optimization of Conditional Value at Risk. It is a measure of risk of loss in investments. The time period is set and the market conditions are assumed to be standard. The most popular application is when big firms use this to gauge the amount of assets they have to cover potential losses. The process of portfolio optimization is to select the best possible portfolio among all objective portfolios depending on some objective. Traditionally, value at risk has been used for this, but it has mathematical drawbacks. To overcome these drawbacks, the authors propose conditional value at risk. Assuming a specified probability level of beta, the beta VAR of a portfolio is defined as the lowest amount for which the loss will not exceed alpha. For beta VAR, this is the conditional for beta CVAR, this is the conditional expectation of losses instead. Let f, a function of x and y, be loss associated with decision vector x and random vector y. X represents a choice of portfolio and y stands for uncertainties that can affect loss. The function f is a random variable in real set. The function p of y is the probability distribution of y in Rm. The CDF psi for a fixed x is shown in the slide. Here, the first formula in the slide represents the left endpoint of the non-empty interval of values alpha such that this cumulative distribution function at alpha is equal to beta. The second formula indicates that the previously mentioned f is greater than alpha, has a probability of 1 minus beta. It is then the conditional expectation of a loss that is greater with the decision vector x relative to the loss being alpha or greater. There are two theorems associated with conditional value at risk. In the first one, the function f at beta of x and alpha is convex and continuously differentiable. By minimizing this function, the beta conditional VAR associated with any decision vector is obtained. We know that for different values of alpha, we can obtain a minima, and this set is now called A. It is non-empty and close-bounded, and the alpha function gives left endpoint of the set A. Minimizing the beta conditional VAR of the loss associated with the decision vector is equivalent to minimizing the function f we saw before over x and alpha. An optimum pair of x star and alpha star achieves the second minimum only if x achieves first minimum and alpha star belongs to the set A. Sometimes, when the set A reduces to a single point, when f minimized over x and alpha, it gives us an optimal solution pair that may not be unique. The x star of the solution minimizes the beta conditional VAR, while alpha minimizes beta VAR. That was the end of the second paper. Now we move on to the third paper. The next paper we talk about is called Coherent Measures of Risk. A set G is defined and it is the set of all risks which are real valued functions on some finite omega. G can be identified with Rn. A risk measure maps the set G to the real space. The total rate of return R on a reference instrument is given, and the risk measure of an acceptance set A is defined as the infimum of set M is defined as the infimum of set of M such that M times R plus X is in the acceptance set of A. The acceptance set associated with the risk measure rho is the set of X in the set of G such that the risk measure of this X is less than 0. We also define coherence as the phenomenon of a risk measure satisfying the axioms of translation invariance, subadditivity, positive homogeneity, and monotonicity. These are brief descriptions of methods used to measure market risk. The first one here is SPAN, developed by the Chicago Mercantile Exchange, and the second one is by Securities and Exchange Commission. Let us assume that the total return of a reference investment is R. The risk measure is coherent only a family of probability measures is present on the set of states of nature, such that the risk measure of X is the supremum of EP times minus X by R, such that the family of probability measures exists in P. The rest of the slide elaborates on how coherent risk measures are represented by scenarios. Now it begs the question that how is a risk measure constructed? To formalize these attempts to measure risk, we can impose margin constraints on certain basic portfolios considered as standard risks. We can use combinations of these risks to support other risks. Finally, since we're bounded by required capital, we use margins required for standard risks. The market price of a security is non-positive if position corresponding to a state of measure omega is a non-positive measure of risk, or in other terms, bankruptcy of the state is allowed. We need to formalize this, so we assume a free market and also denote the closed convex set of pricing probability measures in omega as QR using instrument R. The measure of risk rho b is given and it is coherent. It happens to be associated with R and also B, which is an acceptance set. It is natural to assume that the closed convex set P sub rho of probability measures defining coherent risk measure R has a non-empty intersection with the closed convex set of probability measures, which we had previously denoted as QR. We are finally on the last slide. We talk about constructing measures out of measures on separate classes of risks. Different sets Yj may be exchange-based risk, market risk, or credit risks in a framework where a joint internal model would be looked for. Similarly, multi-line aggregated combined risk optimization tools would call for combined measures of risks. The function Psi may come from preliminary rules given by exchanges and/or regulators.